Actually, does anybody want to work the camera for me? Any volunteers? You'll do it? Can you just, if I put it in front of you, can you?
Yeah, for sure.
You'll be able to see it. Like,
Yeah.
you don't have to follow me. Like, the main thing is to get what I write. No one cares what I look like or where I am. Yeah. All right, so as you can see, Dr. Dinsmore has kindly written for us the big picture of physics. Here it is. 4 fundamental forces: gravity, electromagnetic, strong nuclear, weak nuclear. And so, yeah. I think we covered gravity in this course, but the others will have to wait, right? I don't think, honestly, we don't really have classes on this so much here. Well, okay, maybe there's quantum chemistry, I don't know. But yeah, so these are the current picture of physics is all of the fundamental interactions that we see in nature can be described by one of these 4 quote-unquote forces, all right? So the first order of business in here, well, we'd like to understand what a force is. We'd like to understand how to describe God's creation with, precise mathematical laws. And this is what physics is. Physics is a way of using mathematics to precisely, that's not even a word, precisely describe creation. All right, so the difference between, I would say, between physics and other branches of science is that physics demands like a mathematical account of how things work. All right, so it's essentially a class in math. It's math with lots and lots of open-ended word problems, which is why people love physics so much, because you guys love the word problems, right? But the first concept that we need to master in here is vectors. What is a vector? What's a vector? Anybody know? Now's your chance. A force with a direction. Oh, thank you. Did everybody get a chance to to check the sheet? Oh, one missed it. A force in a direction, it's got a magnitude and a direction, right? So a vector, what it is, if we want to think about it geometrically, right? And that's usually where people start. A vector is a magnitude and a direction. Well, that's not even it. I would say basically a vector is a directed line segment. Right, so we can kind of make a picture of that. Yeah. So something like this, yeah? So you should draw an arrow like this. This is a vector. It has a base point. That's where it starts, right? And it has a terminal point. That's where it ends. I don't usually talk too much about the base and terminal points, but I will just say this. In here, we like to think about being able to move vectors freely around. Like the first kind of weird thing is we say that this vector, and I don't know if I'll do it or not, but I'm going to try this vector. These are the same vectors in the sense that we're going to identify if it has the same magnitude and direction, if you will. If you move the base point but still make the extension of the vector the same, we consider it to be the same vector, right? So here, so I could say this is vector A, this is vector A. We consider those to be the same vector. Like here's another example that's a little bit easier to see. So this vector, and this vector, and this vector, these would all be you'd think I'm gonna run out of numbers to block in North Carolina. I tell you, it used to be that I'd pick it up and it'd be about an extended car warranty, and that was interesting. But now it's always just dead air, So, I've been trying to get that phone to ring over the whole break, like whenever my wife calls me, and it never works. But now, see here. So yeah, so if you need to take if you have to answer your phone in here, just you can pick it up and walk out. That's fine. Like I know you guys got things to answer. I would say generally speaking, laptops being open in here is a bad idea because there's really probably not a good reason to have it open. Not sure about that rule yet. I'm floated out there. If you're actually doing things related to this course, that's fine. If not, then you're distracting people around you. I meant to say that earlier. I'm sorry, I'm just saying that now, just springing it on you. Let's see here. So the idea is that these three vectors, B, 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 these are all the same vector from our way of thinking, because we're basically saying you can move it around. So I often illustrate this by just, making a vector from some markers like this. Yeah. So the idea is, as long as I take the direction of the marker, of the vector, right? And I keep it the same, it's the same vector. We can move it around in space. And that has a meaning, right? We're always just starting at that base point and pointing in a certain direction away, right? Now to describe that precisely, we need to talk about the magnitude and the direction, right? So let's talk about 2 dimensions. So 2-dimensional vectors. So we have A is something like, we use this notation sometimes, A sub x, A sub y, all right? And so let me just kind of make a picture of that. So maybe it looks like this, all right? So why am I putting it over there? That's weird. I'll put it over here. Here's A. Do you like these boards? Some vandal came in and put these in the classroom over Christmas break. I don't know who. Somebody. Probably somebody who likes to write on 3 boards in the semester. Just saying. Can't be sure. It's an odd sort of vandalism, but there it is. So what this means, AX and AY, that means that you go this much over AX, right? And this much up AY. So AX and AY both being positive means that if you base the vector at the origin, right, that you're in quadrant 1. Now, we could rewrite this. So basically the rules of vector addition are like this. I guess I should just define them for you. I don't know, there's a kind of chicken and egg problem here. Do you want to define vector addition geometrically? Do you want to define it in terms of an algebraic rule? However you define it, this much is true. So we can pull AX out like this, and we can pull AY out like that. So AX and AY, these are both numbers. All right. Now, these vectors right here, this is called, I call this X hat, and this over here I call Y hat. Now, a lot of standard physics books, well, instead of calling that X hat and Y hat, what do they call it? I hat. And they call this one J hat, right? Or worse yet, they'll just make them bold-faced, I, J, K. I don't know about you, but I have trouble writing bold in my homework, right? So that's why we've got to put hats on things, because otherwise we don't know it's a vector. So there's a very big difference here. The AX and the AY, these are numbers, or scalars as we call them in physics, whereas the 1, 0 and the 0, 1, which is equal to X hat or Y hat respectively, these are vectors, right? A vector has a magnitude and a direction. So in this picture here, a way to understand what's going on, let me draw it again over here, is that this is really just giving us AX X hat plus AY Y hat. And let me just draw the picture one more time up here. So I guess I'll keep it up here. It's just most natural for my picture. So we're building the vector from 2 pieces. One is like this, and the other is like that. We add them together tip to tail, yeah? So the red one is actually the vector ax x hat. The blue one is actually the vector ay y hat. And so what we're seeing is that A, right, is the tip to tail vector sum of ax x hat and ay y hat. So some language. We say that ax and ay are respectively the scalar components of the vector A. Right? Those are scalar components. These guys here are what are known as the vector components. So this is like the x vector component. Right? And likewise for the y. All right. So let me put some definitions down here, just to be clear. How do we add vectors? A plus b. So I'm saying like ax, ay, bx, by. How do you add vectors? It's very simple. You just add the components. Right, so that's how we define vector addition. We can also talk about scalar multiplication. So this is just the algebraic definition, right? CA is C times AX, AY. So we just do C times the first, C times the second. This is the so-called scalar multiplication. Have I written below the event horizon? Can you guys see it, or am I too low? It's fine. So this is the algebraic rule. The geometric rule, how can you picture vector? How do we picture vector addition? So the idea here basically is just this. You start out with vector A, right? And then we can talk about vector B. Maybe it goes like this, just to give you an example. So to add A and B, what I do is I draw first A, all right? Then I draw B, but I make the tip of A is where the tail of B starts, right? So I'm saying that the base point's the tail. So tip to tail vector addition. So we start, go that. Where is A plus B in this picture? A plus B, the so-called resultant of these two vectors, is over here. This blue vector is A plus B. All right. This is how we add vectors geometrically, tip to tail. You notice I don't even need to tell you, like the numerical components of the vectors. We can still add them geometrically, right? So you could start with that, and you could derive this if you wanted to. What does scalar multiplication mean geometrically? So if I want to draw in this same picture, what would like 2a look like? Where would 2a be if I'm going to put it in red? What's 2a would be like this. So we'd go A, and then go A again, right? So this altogether would be twice A, which of course would also be equal to what? Naturally, it would be A plus A, right? I'm going to put a B there. I'm an idiot. See here, what's wrong with me? So A plus A, again, 2A. Where's minus A in this picture? Yeah, at the origin, but it would just be at the origin. So you're like A minus A would be 0. That's true. But so I'll put minus A down here. Minus A would be like this, right? So you're right. If this picture is getting too busy, let me make a new picture. So like here, this is C, right? What does minus C look like? Just like this, right? Let me put C up here. So what's C plus minus C? 0, right? So you do need to write so I insist that a vector, you either have to write a vector symbol on it or a hat symbol on it. Right? We do not write vectors without a hat or a vector. Now the one exception to that rule I make, and most people do, is that technically this should be the 0 vector in this context. Right? So you might distinguish between 0 and the 0 vector. I'm not going to. I'm just going to say it's 0 if you'll forgive me for not writing zeros, a vector on 0. Let me just say this before I get dragged into some notational quagmire. They're equal, okay? All right, now, what's the length of a vector? See, because this word I use, magnitude, the idea of magnitude is length, right? So what's the length of the vector? We have a symbol for that. I'll give you the definition here. The magnitude of A, which we also denote by A, is the square root of ax squared plus ay squared. So this is the magnitude or length of A. Does that make sense why we should use that? If you look at the picture that we drew earlier, right? What's the length of the vector? It's the square root, right, of this distance squared plus that distance squared. And this formula will still make sense when the ax and the ay are plus or positive or negative, right? This works in quadrant 1. It works just as well in quadrants 2, 3, and 4, right? And remember, you're like, well, the vector doesn't have to be based at the origin, so what you're saying isn't really that helpful, because the vector could be based anywhere. Yeah, it could, but we could just take that vector, we move it back to the origin, and then that picture works, right? So if we can define the notion of vector length at the origin, it's fine. We've got it everywhere. So that's vector magnitude. It was much worse for them than it was for us. Okay. So example 1. Find vector length 1 in direction of, let's say, b equal to -3, 7. By the way, I'm working with vectors which have pure numbers as components, right? We'll soon be using vectors to represent position, velocity, acceleration, forces, all of these different physical variables, right? And when we do that, the components won't just be numbers anymore. They'll be things like, meters per second, a Newton. We'll fill the blanks in of these vectors with numbers that have, physical meaning. For the moment, we're just trying to get used to the mathematical formalism. But for the, also for the moment, just think of them in terms of like directed line segments. I think that's a good place to start. All right. Okay. So, how would you do this? Oh, here I'll show you the trick. All right. So the magnitude of b is what? It's what? Minus 3 squared plus 7 squared. Yeah. So we got what? Square root of 56, I believe. I don't know where my calculator is at the moment. That's all we're gonna have to stick with that. So, all right. So here's the thing: if you let c equal to 1 over the square root of 56 times -3, 7, what do you? This vector. Calculate the length of this vector. What do you get? Yeah.
It's the square root of 58.
58? I can't do math. Oh man. I was just not there. Oh no, that's a hideous 8. Thank you though. This is why we can't have nice things. All right, there we go. That's a 58. Thank you. There we go. Fallen man, what can I tell you? We live in a fallen world. It's true. Calculate the length of this. What happens? You can check. The length of c is equal to 1. This is not an accident, all right? So this thing I just did, I took the vector and I divided by its length. This is called normalizing a vector, all right? And so definition, if A is not equal to 0, then A hat is equal to 1 over the length of A times A vector. So in other words, this previous example that I just did, I calculated the unit vector for B. This is actually, in view of that definition, this is exactly B hat. So that's, why do we need A not equal to 0? So let me prove for you that this works in general too. Let's just take a second here. What are the properties of vector length? I should mention to you. Props. So first of all, if we have the length, this is mostly all we need. The length of a constant times a vector, guess what? It's equal to, you can prove this, the absolute value of the constant times the length of the vector. Now, I can show you in the formula if you want me to see me do it, but I don't think we'll gain much by doing that in here. It's simple to prove this, though. It basically comes from, if you put CA into the formula here, you get a C squared on both of these terms, so you can factor out the square root of C squared. But what is the square root of C squared? It's the absolute value of C. The square root of C squared is not C, it's the absolute value of C. Because square root's always positive, or non-negative, I should say. So that's a rule. And so this is why this thing works. See, because if you calculate the magnitude of 1 over A times A vector, what do you get? You get the absolute value of 1 over A, that's just a number, right? Times the magnitude of A. But this is just another notation for A. And what do you notice about the, what's one of the properties of the vector length? Could it be negative? No. Vector length, the smallest it can be is 0. And the vector length is only 0 for the 0 vector. So if I take the absolute value of a vector length, it's just the vector length again because it's positive, so absolute value is unnecessary here. Just like you guys were thinking a minute ago, right? So 1 over A is just that, and they cancel, and lo and behold, uno. So this is a unit vector. It's a vector of length 1. I finally now have the mathematics to make good on my claim. A vector is a magnitude and a direction. What's the magnitude? The magnitude's A. What's the direction? A hat. That's what it is. And so if you take this equation right here and you rewrite it, what do you have? What's arguably a better way to look at this equation is that this is to say that A is equal to A times A hat. A vector is a magnitude times a direction. The direction we should think of as a vector. Now, that's not always what people do. Why is that? Why do people not always say a direction? Why do people not always use a vector for the direction? If we're in 2 dimensions, what else can we do? So in 2 dimensions, if I have a vector, right, I can write it, maybe it's like here, right? Can you, magnitude we understand, right? That's how far the vector points out from the origin, right? We got that. Sorry, I think this red is bad news for you guys over there, isn't it? Learned that from Dr. Sprano. Let's see here. Did you guys have Dr. Sprano? Calculus 2 right now? No? Before? Previous? Okay, yeah. See, he used to teach Calc 1 here, and so like everybody had him. But so if this vector A, well, the thing, we could also describe it by the standard angle. right? So theta, this is measured counterclockwise from positive x-axis. That's the standard angle, yeah? And so if you look at this, right, we have, yes, ax, ay, but what's the formulas for ax and ay in terms of the standard angle? So this distance here is a, right? And so if you tilt your head and squint, you can see that in fact ax is going to be equal to a times the cosine of theta, and ay is equal to a times the sine of theta. And that would be easy to see in the picture I just erased. Maybe I could do it over here, like this one. If I had a theta in here, you can see it, right? See, this would then become what? A cosine theta x hat. This one would become a sine theta y hat. But the beautiful thing about the sine and cosine function is that their meaning in quadrants 2, 3, 4 is such that these formulas continue to make sense outside of the context of that right triangle trigonometry, which most clearly demonstrates their use. These formulas are good all the way around, right? So what does that mean? That means we can take this vector, right, and we can rewrite it as a cos theta, a sine theta, yeah? And we can factor a out like that, right? And by the way, the unit vector for a given vector is unique. If there is a unit vector for a given vector, there's not like, which unit vector do you mean? No, there's just one. So by process of elimination, we can look at this and say, well, this is also a hat, right? Sorry, Fonzifying this lecture. So you guys don't know who the Fonz is. So it's an irrelevant comment. No? Muppets? No, not Fuzzy Bear. That's different. The Fonz. Happy Days? No? Classic television? Henry Winkler? Whatever. It's not important. The point is, we can cancel these a's and we just find another formula in 2 dimensions for the unit vector, which is this. See that? Or if you want to go back to the x hat, y hat notation, this is cosine theta x hat plus sine theta y hat. So if we want to talk about the direction of a vector in 2 dimensions, we could either describe it by a 2-dimensional unit vector, right? Or we could describe it by the standard angle. What's the standard angle for my my vector over there, minus 3, 7? So we had b equal to what was minus 3, 7. What's theta for this? What's the standard angle? So if you want, we can also use this notation. I don't always use this notation, but I think it's nice to have a notation. Let's say that the angle of A is what we call to be theta, yeah? So how would I figure out the angle here? What do I want to do? I want to draw a triangle. I'm a triangle, right? So minus 3, 7, where is that? That's over here, right? There's a triangle over here. It's got 3 down here. It's got 7 over here, right? Where's theta? Well, theta's over here, right? So if I was to ask you, what's this angle over here? Let me call it beta. What would beta be equal to? You guys know trigonometry, right? You're telling me what theta is, but I'm asking what beta is. Beta is what?
Arctangent of 7 over 3.
Arctangent of 7 over 3. Right. Can somebody tell me the number for that? And we have a calculator handy. I'd like it in degrees. I try to work in degrees here in the most part. Except for when I'm doing calculus, when I always work with radian functions. Yeah.
I think it's negative 3.6339.
No, this should be positive. Inverse tangent of 7/3 should be positive.
1.165.
That's radians, I think.
0.0407.
Inverse tangent of 7/3. Do your thing. Yeah, 0.47, that was radians. Come on, Google.
66.8 degrees.
That sounds right. 66. 0.47 radians? 0.47 times. What? Sorry. So what did you say it was? 66.8. I'll just have to trust you for now. So approximately, right, like that. No, that's not the answer though. That's just beta. What am I asking here? My question originally was what was the standard angle of this vector? What is it though? I shouldn't box this. It's not what I'm after. Yeah, my bad. I was just so happy to have a number. So theta, right, the one we're after, would be 180 degrees minus that angle, right? So the standard angle for this is actually like 113.2-ish, if I did that right. So just a reminder, well, a warning. When we're calculating the standard angle of a vector, we have to be careful about the fact that sine and tangent is misleading. If you calculate inverse tangent of an angle, what are you going to get? Your answers will always be between what and what? Between minus 90 and 90, right? Inverse tangent always outputs minus 90 to 90. Inverse tangent of y over x will always put you in quadrants 1 and 4. But there's also quadrants 2 and 3. And so to get over there, we have to adjust the formula either by adding the reference angle or subtracting the reference angle from 180, depending on whether we're in quadrants 2 or 3. Right, so that's trigonometry, but it's also one of the basic things we're facing here with vectors, right? Finding the standard angle actually requires a little bit of work. Good news, though, these things still make sense for 3 dimensions. So I'm talking about 2-dimensional vectors so far. What's a 3-dimensional vector look like? So this will be my final example for today, since we're, I think, just about out of time here. So if we think about 3 dimensions, we can talk about vectors in 3 dimensions, right? So that would be something like AX, AY, and now there's AZ, right? So what do you think? I mean, I always use this example. I'm talking about 3 dimensions. So I think of like upwards as Z, right? And then maybe that's the X direction, and that's the Y direction, right? So I need to make that the X, and that's the Y for reasons that I'll talk about later. And then this would be Z. And then the origin could be this point right here, all right? So I'll try to remember to bring my laser in next time so I can take some coordinates in here. Because I can point the laser at your forehead, you close your eyes, and then I'll take you, I figure out what the distance is from you to the thing. These laser tape measures are great. But some of the things I'm talking about right now still make sense in 3 dimensions, like this one. If I had 1, 2, 2. So here's a vector. What's the unit vector for this one? It's still 1 over a hat. What's the length of a 3-dimensional vector, though? It's the square root of the sum of the square of the first one, the second one, and the third one. We can draw a picture to explain why that is, right? So if this is my 3-dimensional vector, it's got 3 pieces, right? It's got the AX X hat piece, it's got the AY Y hat piece, and it's got over here the AZ Z hat piece, right? And so in this picture, by the way, this and that are the same. I just hardwired. I can't fix it. It is what it is. But in this picture, if you put the shadow of A down into the XY plane, you get this guy, right? So the length of this down here would be the square root of ax squared plus ay squared, right? See that? This is a right triangle. And then if you look at the vertical triangle, it's one of its sides is square root of ax squared plus ay squared. The other side has length az. So what's the length of a? It's the square root of ax squared plus ay squared squared plus az squared, which is, of course, this formula. Now, there used to be a fellow who worked here who he get really upset when people would derive this, because he said, this is a definition. It doesn't have to be derived. And he's right. I mean, that is the definition of vector length, but this is why it's plausible as an extension of the two-dimensional thing. Because if you look at a three-dimensional vector, you can see two two-dimensional vectors, two-dimensional triangles, which lead you to this formula. So that's the formula for the length of a three-dimensional vector. You just take the sum of all three squares to square root it. So what's the unit vector for a then? What's the length of this vector, a? Yeah, it's 3. So 1 squared plus 2 squared plus 2 squared, also known as the square root of 9, which is, like you said, 3. So a hat is just 1/3, 2/3, 2/3. And you can check it out. If you take 1/3 squared plus 2/3 squared plus 2/3 squared, that gives you 1 plus 4, which is 9 over 9, which is 1. So that, in fact, is a unit vector in the direction of 1, 2, 2. Any questions? Listen, so next class, I'll start with the dot product, and I'll explain to you that's an even better way to find angles between vectors and everything. So this is just the start. But anyway, I hope that made sense.